Means hello students, how are you? Today we will start the part 5 of the projectile motions. Okay. At first, in part 4 we have already studied the applications of the relative velocity in the projectile motion. Now it is the second example of application of relative velocity. Second example means there are two height, h1 and h2. Okay, there is some height difference. Okay. One of the projectile is thrown from here and another projectile is thrown from here with initial velocity u1 and u2, okay, and with some angle theta. This is the horizontal component, this is horizontal, no vertical component, and these has vertical components u2, y in downward directions. So at first, two conditions happen. Two conditions may be happen. Number one, collisions takes place. Number one, collision takes place. Okay, takes place. And number two, no collisions. No collision. At the time, you have to find the minimum distance between the two projectiles. That means we have to find the minimum distance between these two projectiles. If the collisions not take place, okay. So at first, if collision take place, what is the condition? That first you find u1x, u2y, okay, u2x, u2y, u1x, that is u1x, that's mean u1, u1y, that's mean 0, no, because particle is thrown here, this is 0, u2x, this, okay, u2 cos theta, and u2y means minus u2 sin theta, okay. Now find the v1x and v1x, v21x and v21y, okay, that's the relative velocity. v21x means both are moving towards each other, so we add these two components, u1x and u2y, that is u1x plus u2x. And this is only u2y. This is only u2y minus u2y. Okay. No u1y. Okay. That is. So we get the component of the relative velocity. Now we can draw the direction of relative velocity. That is the direction of relative velocity. 2, 1. This is the particle 1. This is the particle 2. This is the direction of relative velocity for collisions must be happen. Okay. And this angle may be alpha. So you can write tan alpha equals to, that is v21y by v21x. Then you get the direction. Okay. Or that is equals to total, this is h2. Okay. This is h2 and this is h1. So height difference is h2 minus h1. Height difference is h2 minus h1. That is h2 minus h1. Or this is, suppose it is d. Suppose it is d. Then this is d. So we get h2 minus h1 by d. That is also the value of tan alpha. That is also the value of tan alpha. So tan alpha is ratio of the two relative velocities along y-axis and x-axis, and the height difference divided by d. That is the conditions for collision. If the collision takes place, okay, then you can find everything if the question is asked from these conditions. Okay, if the collisions takes place, that means particle 2 just come out on the 1 and the collision take place. But if the collision do not take place, then what happens? To just move away, from some distance from 1 and some distance from 1 in downward or in maybe upwards. At that time, the question is asked, what is the minimum distance between these two projectiles when collisions do not take place. So that is the second case, and we will discuss here this second case if the collision do not take place. If the collision do not take place, then relative velocity of the two, just like that is the column 1 and column 2, this is h1 and this is h2. Here particle 1 is present, particle 2 is present, and this should be the V21 or maybe the V21. Okay, that's you know the theta. This is you know alpha. Already you know it, alpha. But V21 may be this or may be this. So if you draw perpendicular from this point to this and this point to this is the minimum distance. This is the minimum distance between the 1 and 2 in the throughout the path. And this is asked in the question. Okay. So how can you find this minimum distance? Now you have to find, you know this is h2 minus h1, okay, and you know d, this is you know, so you know this distance, you know this distance from Pythagoras. From Pythagoras you easily find this distance. Suppose it is b and it is a, then ab equals to root over of h2 minus h1 square plus d square. So you know the distance AB. Okay? You know the distance AB. Now you want to find this angle. If it is alpha, it is 90, total is 90 minus alpha, and you have to find this angle beta or this angle. If the particle moves this, then you find this angle. If the relative velocity moves in this direction, then you have to find this angle. Okay? And sine beta, if you know beta, then sine beta equals to perpendicular by hypo, and that's perpendicular is nothing but minimum distance AP by AB. So only we know, if we know the sine beta, then we get the minimum distance AP. Okay? So how can you get beta? That beta, tan beta equals to perpendicular by base, or sine beta equal to perpendicular by hypo. Now find this velocity, you know this velocity, and this velocity you know already, and you know the components of these two velocities, of this velocity is v21x and v21y. So if this move in this direction, and if you know the x and y component, then you know this angle. You come to know this angle. Suppose it is theta 1. And what will be theta 1? Tan theta 1 means perpendicular by base. That means horizontal velocity v21x, v21x by v21y. That's you get it, tan theta 1. So now you get. Now you know tan theta 1, that means you know theta 1, and if you know theta 1, then you find the value of beta. Beta means 90, a total is 90 minus alpha, minus theta 1, and that is the beta. So this is the angle beta. You know alpha, tan alpha equals to, you know alpha from this here, tan alpha equals to h2 minus h1 by d. So you know alpha, tan alpha. And now you know tan theta 1, that is v21x by v21y. And now you come to, you know beta from this formula. You come to know from this formula. Okay? We are going to solve this total phenomenon by this method. And you get beta. And now sine beta equals to AP by AB. And AP is the minimum distance between these two projectiles if the collision do not take place. Okay, clear concept? This is the second example of the application of the relative velocity. You can apply relative velocity. Okay, very fantastic concept. Now we start the application of the reference frame in the projectile collisions. Reference frame means you generally we throw a stone from the ground, but now we are on the plank, and plank is moving with velocity v, and we are throwing here u is nothing but u r with respect to this, and we make an angle theta. So we get the two component u cos theta and that is u r sin theta. That is the trolley. Trolley is moving with velocity v on the ground. Trolley is moving with velocity v on the ground. Okay? And we get the two component of the relative velocity because we throw the particle with respect to trolley. So this is the relative velocity of the particle. And you get the two components, you are cos theta and you will say theta. Okay? And trolley is moving in a horizontal direction. Suppose a man standing on the ground. So with respect to ground, what is the x component of the velocity and y component of velocity? With respect to ground, the x component velocity ux should be, this is relative velocity and this is the absolute. So how can you get the absolute? Another absolute. V minus u r cos theta or u r cos theta minus v. U r cos theta minus plus v. In the same direction, vector additions takes place because 0 degree angle. Because we know V12 means V1 minus V2. If you want to find V1, then it is V12 plus V2. So that's the concept. Yeah, this is relative velocity. So this is the relative velocity and absolute. And you get the absolute ground frame. U r cos theta plus V because they are in the same direction. Okay? And Uy is nothing but u r sin theta. U r sin theta. So time of flight of the projectile will not change here. 2 u r sin theta by g. And range equals to ux. That's when u r cos theta plus v into total time of flight. That's the range as seen by this man. As seen by this man. This is the concept of change of reference frame. It is called the reference frame concept. Okay? Reference frame. Yes, trolley is moving on from the trolley. You are throwing the stone. Here trolley is only velocity. Okay? Reference frame maybe have accelerations, maybe velocity in opposite direction. So you can take any type of reference frame. Trolley is moving here rightward. Now you can take trolley moving in the leftward. That means in the another example, we take trolley. That's the trolley is moving in negative direction. That is V. And now you are throwing the stone here, you are, and making an angle theta. That's very possible. And here at that time you are cos theta. This is minus v. This should be minus. Because trolley is moving in the opposite direction. This will not change. Your sin theta will not change. So time of flight will not change. Okay? So range should be changed. You are cos theta minus v into t. Okay? You are cos theta minus v into t. That is the first application of the reference frame in the projectile motions. Or you project the motions in a lift. Lift means another kind of reference frame that is also moving with acceleration A. Lift is moving with acceleration A in upward direction. Okay? But from inertia motion we know particle do not get the acceleration but particle get the velocity. Whenever you are jumping from the moving bus, suppose you are jumping from the moving bus, you are jumping from the moving bus, you are getting only the velocity of the bus. You are getting only velocity of the bus. You do not get the acceleration of the bus. You do not get the acceleration of the bus. You only get the velocity. Okay. That concept should be applied in the lift case. Because suppose the lift is moving upward with acceleration A and you are projecting a particle U with respect to lift. Because at that time when t equals to suppose after t naught. So velocity of the lift equals to a t naught. Okay? And you are throwing the stone. You are making an angle theta. That is ux equals to u r cos theta. And uy equals to u r sin theta. But it is the velocity with respect to lift. And lift has velocity at that time a t naught. So with respect to ground, man. This is with respect to ground. Ground man, with respect to ground man. What will be the velocity of the projectile? Ux will not change because lift is moving upward. Only uy will change. So ux just like u r cos theta. And uy, lift is moving with velocity a t naught. And relative velocity is also in the same direction. So what will be the absolute velocity? A t naught plus u r sin theta. A t naught plus ur sin theta. This should be the uy. This should be the uy. So time of flight, yes. Whenever you throw the particle and particle in the air, in that time no effect of acceleration. No effect of accelerations present on this particle. So you can find the time of flight by 2uy by g with respect to ground. But with respect to lift, time of flight 2ur, that is 2ur y, 2ur y, ur sin theta, divided by particle acceleration g. Particle has acceleration g and lift has acceleration a, that is a plus g. 2ur y by g, that is time of flight of the projectile with respect to lift. That is time of flight of the projectile with respect to the ground. With respect to ground, okay? That is the concept. With respect to lift, with respect to ground. That is also change of reference frame or application of the reference frame in the projectile motions. You can easily understand if you know the applications of relative velocity. Then relative velocity application and reference frame application are correlated. Okay? Are correlated. Clear? So for different kind of reference frame, whenever you tackle with different kind of reference frame, maybe in horizontal motion, suppose you are inside the train is moving with acceleration a, you are throwing a stone inside the train, then what happens? Whenever you throw the stone particle in the air, then particle only gets the velocity of the train at the time of throwing. Particle will not affected by the acceleration of the train. Okay, so whenever you should alter the velocity of the particle whenever it is thrown. At that time train has some velocity and you can change the velocity horizontal directions when you take the velocity with respect to ground. If the train is moving, I just give you this example, okay? From this example you get, this is a train, train is moving with acceleration a. Suppose a particle is thrown here with relative velocity ur, making an angle theta, and particle just land here. Suppose this man inside the train moves. Suppose this man who throws this stone moves inside the train by distance s0. Suppose this is s0 and man has to move the distance s0 inside the train. Then what will be the relations between this s0? A man who is inside the train. Man is inside the train and who throw the stone, okay, with velocity ur, making an angle theta, and it is land here. And man moves to catch it in the same height. Very possible, okay. Man moves inside the train to catch the particle, and man moves by, suppose s0. Man moves the distance s0, and it is moving with acceleration a. It is moving with acceleration a. Man always feels this acceleration because man is inside the train, okay? And this projectile will not feel any acceleration. Projectile has no acceleration because projectile is in air and it has only g and it is not along x-axis, it is only along y-axis. So you can equate the distance, equate the displacement of the man and the displacement of the projectile with respect to ground. With this, the displacement of the man, half a d square ut plus half a d square, or displacement of the projectile. Projectile displacement means total time. Projectile has no acceleration, so only ux into t, that is the time of flight. Time of flight means 2uy sin theta by g. That is uy means ury, and ux means absolute velocity with respect to ground. So ux means urx, that is ux means relative velocity x component urx cos theta. And if train start from rest, then no velocity of the train we do not take. If train has velocity, then it should be added. in just in the previous example. So that is u rx ux into t. T is the time of flight. Then sp and s man has velocity.